Diving in to 5.4 and 5.5. All these two sections are is story problems and applications of linear systems. So the main types of problems that we are going to be seeing that show up in these sections and on the homework are equations that are like the ones we have listed here. The total cost of something being the variable cost plus a fixed cost, the distance equals rate times time equation, or our DIRT equation. Mixture problems, yes, bucket problems, they are making their inglorious return, I guess would be a way of describing it, but they are absolutely coming back. Remember that that is the rate of concentration times the amount of a mixture that we have, and we have a setup for this that we can use. We also get, goes along with the distance one, but it's a more generalized version of that. It's referred to as the rate principle. And this simply is an amount of something is equal to a rate times a base. Generally, that base is a time. But this is a, again, very generalized way of looking at something happening over a period of time or over some base amount of something else that we're tracking. So I think the rate principle is one that's probably the most difficult to one to see and use as we're going through this material, specifically because it's so abstract in how it sounds that how do we see that in application? How do we track that and so on and so forth? But we'll have an example of it and we'll go through how to set it up and solve it and all of that. And then the last one that we have showing up here, this is one that is a bit more niche and we don't necessarily use as many of our previously learned methods for it, but it's calculating our GPA. And the general equation and the thing that we use for that is it's the sum of our grade points. This is the grade that we got and the number of credits that were attached to that particular class or that grade that we have, all divided by the sum of, or the total added up amount of the credit hours that were taken. So standard notation, we see it as is sigma grade points, which is, again, sum of all grade points divided by the sum of all credits that we've earned, and that equates to our overall GPA. Now, as listed previously, and we've talked about previously in the class, our strategies for story problems, read, reread, and reread over and over again. The more that we do that as necessary, the better, especially for setting these things up and going through and getting to our answers, making equations, making pictures with these things, using buckets, using tables, using diagrams, things like that. All of that are fair game. You want to be using those. Make sure that you are definitely taking extra time to label variables and numbers accordingly. Again, I stand by labeling, especially with units, is going to be the most important part of all of these problems, especially with mixture problems. And I'm telling you now, there will be mixture problems on test 3 for our class this quarter. So just as the heads up on that, those are coming back. So let's go ahead and dive into our first problem that we have here. So if you guys need to or would like to, take a screenshot of this, or bring up your phone and take a picture of the screen. We are going to take a look at example 1 here first. But I want to give you guys a minute to go ahead and get that quick picture for yourself as we're referencing this. I'll be putting all of the notes and work and whatnot off to the side here, but I can't exactly do that with all of it on screen right now. So if we take 30 seconds and go ahead and get that. Okay, so with our first example, we are told Dr. Cox orders a dosage of 40 milliliters of 16% saline for a patient. Since JD doesn't know how to do his job well yet, he panics and grabs a bag of 20% saline and another with 4% saline, not knowing what to do with them. In a fit of rage, Dr. Cox fumes off to solve the problem for himself. How much of the 20% saline and 4% saline does Dr. Cox need to mix to get the correct dosage for the patient? So we have a classic mixture problem showing up here with our percentages and amounts and things like that. So bringing us over, jump over and get some space to write this all out. So for number 1 here, again, we are mixing things, so we want to set up and create these. I think it's easiest to go through and create the buckets for ourselves. Now, again, you are welcome to use other methods of organizing this if you would like to. I saw a couple people use tables on the test to help out with that, and you may do that. For me personally, I think buckets make the most sense. That's how I keep track of them, and it's easier for me to track stuff accordingly. So we start with our general, a bucket plus another bucket equals a remaining bucket or resulting bucket. Remember also that when we're doing these, we need to have a label up top above each of the buckets. They each need to represent something. And then we need to have a label off to the side of the buckets and then a label for things down below the buckets. So I have 3 buckets and I have 5 labels that need to happen before I do anything else. I'm going to move this over just a little bit so I have some space to write things. Now, as the reminder with these, whenever we are setting these up, we always want the last bucket here to be labeled as the result. So we like to use total for some of these things, but I tend to find that result is a better one because we don't always have percentages adding up in the way that we think they do and resulting the same way that we would think they would. So result going over the last bucket now and forever for all of these. So we now need to determine what are the 2 things that we were mixing together. Well, we were told he grabbed 2 bags of saline. One of them was a 20% saline and the other was a 4% saline. So if you would like to, you have some options on how you could label these things. I'm going to label this first one as the 20% saline bag. And the other one is going to be the 4% saline bag. You could also just as easily label this as bag 1 and bag 2, or bag A or bag B, something like that. Whichever works, you're welcome to use. Now, the other staple that we want to use with these mixture problems is off to the left side, measured inside of the buckets. We want to put the amounts of things in here. So I'm labeling in amount. And then what units am I using with this? Am I using liters? Am I using gallons? Am I using fluid ounces? And as I'm looking at the problem in the first sentence, we're told he orders a dosage of 40 milliliters of 16% saline for a patient. So no numbers yet. We want to put the amount and we're listing the units as milliliters. So perfect. We have an amount and we have a unit with it. Now, the last part, and this is the one that got a lot of people on test 1, and I'm telling you right now, we want to get in the habit of doing this. And if you don't want to label this, then test 1's struggles with this are going to come back. We then have the concentration listed for below the buckets. And again, when we are doing the concentration, we must be hyper specific on what specific percent am I tracking. Now, in this problem, we were only given 1%, and that is percent saline. We do not know what else is in that, each of those bags of stuff. It could be water as a portion of it. Another portion could be antibiotics. Another portion could be morphine. Who knows what's in those other parts of it? But we want to be very specific on what is the one and only percentage that we are tracking in the problem. And I will once again let you know now, on test 3, there are going to be mixture problems that are going to have multiple percentages in them. We are only going to track a single one specific percentage for the entire problem. And in this case, we are tracking the percent that is saline. So down below here, I'm going to write in percent saline. That's all I care about. Any other percentages, are completely useless to us. They are irrelevant. We ignore them. Give them a big, cross it off or put an X or something by it if you need to. It's worthless information. Ignore it. Now that I have my 3 labels up top, my 2 labels off to the side, I can now start filling in inside the buckets and below the buckets with information. If I don't have those labels, I can't fill anything in. So, what information have we been given? What can go where? We were told that the order is for 40 milliliters of 16% saline. That's going to be the result. We want 40 milliliters, and we want that to be 16%, to make that a better 16% saline. What do we know about the other 2 bags and what other information we could fill in? Well, we were told that the first bag is going to be 20% saline. The second bag is going to be 4% saline, so we can fill those in there. Now, the problem is asking us how much of the 20% and 4% saline does he need to mix? So I do not know what the amount is for the first bag. I do not know what the amount is for the second bag. Based on what we've done previously, we would fill in one of these with a variable, and then the other one is some leftover amount where we do 40 minus something there. However, now that we have the substitution method and the elimination method under our belts as something that we can use from 5.2 and 5.3, we can instead list each of these as their own individual variables. I can say, how much of this first bag do I have? I don't know, but I'm going to go ahead and label it as X. So I have X milliliters of the first 20% saline bag. How much do I have of the 4%? I also don't know, but I can write this in as Y. So some amount X, some amount Y. Now I have the entire picture set up for myself. It's labeled, it is clear, and now I can start making equations. What's really nice about this setup, and we're using it again like we did previously, for making equations, the amounts always add together to give us an equation. If we're noticing what we have here, we've got the percent, or an X amount plus Y equals 40. So it's really nice there to make one equation for ourselves. Our first equation is therefore going to be X plus Y equals 40. I have 2 unknowns, X and Y, so I need to make 2 equations to solve this thing. Now my second equation, this is again a universal part for all of these mixture problems. My second equation is going to be, this is for all of them, the first amount and the first concentration multiplying together plus the second amount and second concentration multiplying together equals the third amount and third concentration multiplying together. So I can go ahead and write each of those in down below. We do need to take a quick moment and rewrite the percentages into decimals. We'll do that here really quick. And now I can make those, make that second equation. I'm going to have 0.2 times X plus 0.04 times Y is equal to 40 times 0.16. And now we have our 2 equations. And I do recommend to everybody, if you're asking or noticing or thinking, well, hold on, couldn't I just multiply these 2 numbers together to get a single number? Yes, you can. I am telling you now, write it out first. If the first test is any indicator, we need to make sure we just have the correct original equations before we move on and actually do some calculations afterwards. So once we have that set up for ourselves, now we're presented with 2 equations with two unknowns. I'm going to move this over just a little bit so I have some space to label it. Okay, so we have equation 1 and we have equation 2 over here. Now, we have gone through, and in the 5.2 material, we learned how to solve systems of equations like we have here with the substitution method. You guys also covered yesterday with Adrian, or you weren't in class. Hopefully you watched the 5.3 recording of it. The elimination or addition method. I will let you know right now for our class this quarter and all future quarters who may be watching this this recording, I am not going to require that you use one method to solve this over another. So if you really like the substitution method, go ahead and use that. If you really like the elimination method, go ahead and use that. I am perfectly happy with whichever one you would like to use. Both will get you to the exact same final answer. But let's go ahead and get into actually solving this thing. I'm going to use the substitution method, and I'm going to take this first equation, and I'm going to solve this for y. So I'm just going to get y by itself. In doing so, this becomes y equals 40 minus x, or negative x plus 40, either one. And then I'm going to substitute that into my second equation for y. So I'll bring us down here. And I'm going to end up getting, there we go, 0.2 times x plus 0.04. And I'm no longer using y. This is going to be 40 minus x. And then it equals 40 times 0.16. Now I have one equation with one unknown in it, and I can go ahead and solve this thing for x, work this down and find our answer just like we have previously. So I will let you guys do that. I'm going to work through this as well. I'm using a calculator for all the calculations, but I'll try and show the steps, distributive property, and everything otherwise. I'm getting that I have 30 for x. If we come back up to our picture here, I'll try and zoom it out a little bit. So we're seeing that x represents the amount of the first solution that we have, the first bag that we have. And we can then use that to help us find y. Oops, there we go. So I can put right off to the side. I'm going to go ahead and plug this into equation 1. That seems like it's the most straightforward. I'm going to have 30 plus y equals 40. I subtract 30 from both sides. And I get y equals 10. We can go ahead and write out for ourselves our final answer. So we're going to have 30 milliliters of 20%. Oops, 20. And then 10 milliliters of the 4% saline bag. And there we go. We have our final answer written right in there. I'm going to try. Oops. So I can get the highlight going here. There we go. Again, I use the substitution method for solving this, but you are more than welcome as you see fit on the test or on the homework or any of these story problems. You may use any method that you would like to go through and solve these things out for yourself. I'm going to try and give the overall problem right here. We need to take a screenshot or anything with that. So with this, we'll go ahead and move on to our second example. Again, this is recording, so you will have access to this after class, and I'm happy to bring this up later on as well. Let's go ahead and jump into our second problem that we have here. And again, I'm going to try and go at a reasonably, maybe slightly faster pace because I do want to make sure we get through stuff and have time for questions afterwards. So for number 2, we're told that Michael, Franklin, and Trevor are attempting to get away from a local motorcycle club. They decide to lose the motorcycle club members by taking 2 boats from the same dock and splitting up along a river. Michael and Franklin take 1 boat and go up the river. Trevor takes the other boat and goes down the river. The 2 boats have identical top speeds in still water. After 3 hours traveling at the boat's top speed, Michael and Franklin are 8 miles up the river, and Trevor is 24 miles down the river. Determine the speed of each boat in still water and the speed of the river's current. So what this means, again, we'll draw a little picture of this because I think it's helpful to see this. So if we have our, here's our little river showing up right here. We have a little dock, something like that. And we're going to have, we'll do it in red. So we've got 1 boat, high quality boat drawing over here. And then we've got another boat, do this one in green because why not? So one of them is going upstream, the other is going downstream. Now the river itself, we all have seen a river. And rivers are going to flow one way. So we're going to just say for our picture, we're going to say that the river is flowing in this direction. So it's going left to right on our picture here. So what it's getting at is we have both of these boats have the same top speed. However, one of them is going against the current and the other is moving with the current. So the current is therefore going to have an overall impact in how fast each of these boats are able to move or their rates that they are able to travel at. And we do need to take that into account as we are going through and solving this problem. So we do have a distance rate time problem showing up here. So we're going to make our table for ourselves like we've done in the past. So we have our distance column. We're going to have our rate column, make this a little bit higher here for units. And then we're going to have the time column at the very end. Now like we've done in the past, we do need to have labels in this as well. And then we can start filling this in with other values. Go ahead and erase some of this here so we're not using bunch of extra unnecessary stuff. There we go. That's a bit nicer. So what am I using as units for distance? Well, we were told some amount of miles up the river and down the river. So our units for distance is miles. Well, I don't necessarily know what the speed units are, but we're given the time is in hours. So we can reasonably assume that miles per hour is the rate that we're going to be using, and that's perfectly fine. Now we have 3 things we need to fill in for our rows here. So we have 1 boat, first one here that's going upriver, and we have a boat that's going downriver. So you could label this as boat 1 or boat 2. I'm going to go ahead and label this using the names that we were given in here. So Michael and Franklin take 1 boat and go up the river. So I'm going to go ahead and do Michael and Franklin, just N and F for that first boat. And then the second boat was with Trevor. So we're going to go ahead and just write in Trevor. down there, make that a better V. There we go. And again, as we've done with all of our distance, rate, time problems, we always like to have the last row be total. We put the question mark in there. Maybe we use this row, maybe we don't. We will see what the problem tells us. I'm looking back at my problem, and I start filling in spots in these top 6 boxes. All of them should be filled in with something, either a number, a variable, a combination of numbers and variables, but something in all 6 of those. So looking at the problem, we're told after 3 hours of traveling at the boat's top speed, so it looks like they left at the same time. They both have a time of 3 hours, so we're good there. We're told Michael and Franklin are 8 miles up the river and Trevor is 24 miles down the river. So there's my distances for each of them. Michael and Franklin have a distance of 8 and Trevor has a distance of 24. And now we get to the rate, which is the really tricky part with these. We were told that the boats, I'm trying to look for it here, the 2 boats have identical top speeds in still water. Now, if we're looking at our picture, we know one of them is going with the current, which we don't know its value, and one of them is going against the current, and again, we don't know the current value here. We're assuming both of the boats are going full bore, top identical speed, but one of them has the current going with it, and one has the current going against it. So Michael and Franklin going upriver, they're going to have what's listed as, we're going to list it as the rate of the boat minus the current of the river. And we're just going to leave that as C. Trevor's going downriver, so that's going with him. So it's the boat's rate plus the current rate. So as we're seeing this, R is the top speed of the boat, and the current is taking away from that speed for Michael and Franklin. And for Trevor, the current is adding to that top speed, which would make sense why he's gone so much further than Michael and Franklin have. Now, is there anything in here that tells us I need to know the total distance? Like I'm adding these distances together, or I'm adding the times together? And no, it doesn't look like there's anything like that in there. So we can go ahead and just put some lines through these and say, yep, turns out we're not using the total column or the total row at all, and that's fine. That still happens from time to time in these problems. Now I have distance, rate, time. I can make my equation for myself and say, here's my, whoops, try and do this in blue here. Distance equals rate times time. We can pull these equations right out of what we've written here. So for the first equation for Michael and Franklin, we have 8 equals, and then do the entire current, or the entire rate, times the entire time. For Trevor, again, the distance equals the entire rate times the time. And we're seeing here, hey, now I have 2 equations for my 2 unknowns. I can go through and now I can solve this thing using either the substitution or the elimination method. I'm going to go ahead and let's see, rewrite some of these things off to the side here. Oop, seen a chat. Yeah, so the rate. So the rates that we have here are this. We have 2 rates showing up in this problem. We're asked to find the rates of the boats and the rates of the current of the river. So both of these boats have the exact same identical top speed. That's verbatim from the problem. The 2 boats have identical top speeds in the water. One of them is going against the current because we're assuming the current is flowing left to right here. So if it is going upstream, the current is working against it and is therefore slowing it down. That's where we're getting for Michael and Franklin here. The rate of the boat minus the river current because they are moving against that. We could put another arrow here that's pointing in that direction. So they're moving to the left, the river is flowing to the right. it's working against each other. So that's where I get a reduced top speed for Michael and Franklin. For Trevor, he's going downstream. So the boat itself has the same top speed as Michael and Franklin. So that R is the same as both of them. However, the river's current is going with him. So that is going to speed him up. And that's where I'm getting this R, which is the boat speed, plus the river current and the current speed adding together in this part here. Does that clarify? Question regarding where the rates are coming from our picture? Hopefully. Okay, perfect. So now that we have our equations here, I'm going to go ahead and rewrite them down below. We can go ahead and distribute the 3 through from both of these. So I'm going to rewrite down below here, just so I'm kind of sort of saving some space. Don't need to worry about, paper on here. It's just digital paper. And so again, I'm just taking the 3 and distributing it through to everything inside of each set of parentheses. And again, I have my system of equations here. I'm actually going to move this over just a little bit, so I can label these as equation 1 and 2 here. Now, again, it is our choice. We can use the substitution method or the elimination method to find R or C first. Doesn't matter which one we use. It is completely and entirely your choice on which one you would like to pick. I recommend to everybody be familiar with and know how to use both of them, because you might prefer one over the other, but one might actually be a faster process to use in a given problem. For this one, I am noticing that for my C's, they have additive inverse or equal opposite coefficients. One's a +3, one's a -3. So if I use the elimination method here, I might be able to get to my answer even faster, because I can get my C's canceled out, and then I can use R to solve what's left over. Let's go ahead and do that. I'm going to use the elimination method here. So I have 8 equals 3R minus C, or minus 3C. Oops. 24 equals 3R plus 3C. And again, I'm adding these equations together, so I'm adding things vertically. I have 8 plus 24. That's going to give me, I think that's 30, top of my head. I should probably use the calculator that's sitting next to me, because, that would help. Oh, it's 32. Yeah, slightly off. Okay, so I gotta have that there. I then have 3R plus 3R. I can just add those vertically. That's going to give me 6R. And then -3C plus 3C, well, those cancel entirely. That's what I wanted. So those are gone. And I'm left with 32 equals 6R. Can divide by 6. I'm getting, let's see, 32 over 6. Math Frank, what does that work down to? Oh, it's going to be a gross decimal. Okay. So because we are working with this here, let's go ahead and for this problem, oh, I don't have it written in here. Dang, that's a error on my part. So let's go ahead with this problem. Let's work with these with decimals. Let's go ahead and round to 1 decimal place. So 16 over 3, I can rewrite this to be 5.3 for R. Now, again, it would continue on, but again, we are arbitrarily choosing that we're going to go ahead and round this to 1 decimal place. On the test, if I was going to ask you a question like this, I would be noting round to 1 decimal place, 2 decimal places, blah, 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 something like that. So it's not listed in this one, but on the test, you will not need to guess at that. That will be given to you. But great, now I know my R value, and we have R representing the boat's rate. So I can come back up here. Since I know R, I can plug that in and find what C is. So I'm going to choose to arbitrarily plug this into equation 2. You can choose equation 1 if you would like. Both work. It's your call. I'm plugging into equation 2, and now I'm going to solve for C. And I'm getting that C is 2.7. Awesome. So what I can do now, again, we always want to make sure we're doing this. We're saying the boat speed, because we're asked for both of them. So the boat speed is 5.3 miles per hour, and the river current is 2.7 miles per hour. And there we'd have our final answer for this problem. Again, I chose to use the elimination method to solve this. On the test, you can use whichever method you would like. I will not be requiring one over another for any of the story problems on test 3. We'd have our final answer right there. Try and get the whole thing in here for a moment. Might be zoomed out a bit, but hopefully, yeah, there we go. Okay, let's take a look at example 3 here. We are told that Jeff and Ryan are building a new stone castle in Minecraft together. Because it's going to be massive, they determine they need to take 2 days to assemble all of the blocks of stone they need. On the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone. On the second day, Jeff worked for only 3 hours and Ryan worked for 5, for a combined total of 2,805 blocks of stone gathered. Determine how many bricks per hour Jeff and Ryan are individually able to gather. Okay. So in kind of a weird one, not showing up here, but this is where we're going to see the equation for rate come into play. So I'm going to scroll us up there to our first page. So this is where we see the rate principle come in. We have some amount of stuff based on a rate times a base, so a number of days, a number of hours, things like that. So we're going to be using that here for this particular problem and building stuff for each of the days. And I think it's helpful to work with this as we have a first day and we have a second day that we can put together. So let's go ahead and bring this over here. Let's start building some equations with this. So we have some information regarding day 1, and we have some information regarding day 2. Once again, we want to try and break these things down into smaller, more controlled parts, and I think they become easier to set up and solve that way. So what do I know about the first day? We're told on the first day, they put in 4 hours of work each and collected a combined 2,500 blocks of stone. Okay. Working with that, we know that they each worked for the same amount of time. They both worked for 4 hours. However, we don't know what their, we'll call it mining rate is during that time. So we can think of it like this. Again, using that rate times a base amount. We can think of they have a combined total of 2,500 stone blocks between them. We know that Jeff worked, and he works in mines at some rate, and we know that Ryan works at a different rate. One's faster, one's slower, but we don't know that at this time. What we do know is that Jeff worked at some rate for 3 hours. So we can write this in as the rate of Jeff, which we're going to use as G, times the time that he worked, which was 3 hours. So this is the total amount of stone that Jeff gathered. So we have Jeff's total plus Ryan's total. And Ryan's total is going to be his rate times the time that he worked. Once again, I don't know what Jeff's rate is. I don't know what Ryan's rate is. That's okay. We're just starting to build equations here. So as you're looking at this and you're thinking, well, this kind of looks like the distance rate time problem, but kind of different from that as well, you'll be spot on with that. We have a total or an amount equals rate times time plus an amount equals rate times time gives us a total amount at the end here. Now again, we have two unknowns. We have G and R, which means we need to have two equations. We have our first equation. Let's go ahead and make our second one. So for day 2, the problem states, on the second day, Jeff worked for only 3 hours and Ryan worked for 5 for a combined total of 2,805 blocks. Oh, and I'm seeing an error. On the first day, they both actually worked for 4 hours, not 3. So error on my end. I glanced down and saw a different number. So slight adjustment there. The first day, they worked for 4 hours each, not 3 hours. Apologies there. Now for our second day. Again, what's their combined total? Well, we know that's 2,805. Can put that in. So the combined number of bricks they each found, or blocks, or whichever. And then we have Jeff listed in front. Let's go ahead and keep Jeff in front. So we know, and we're going to assume that he worked at the same rate as he did on day 1. However, he worked for only 3 hours on day 2. And Ryan, again, we're going to assume worked at the same rate, but he worked for 5 hours on day 2. And now I'm seeing here, now I have two unknowns and I have two equations. This thing is officially set up, and I can go ahead and solve this however I would like. So I'm just going to rewrite it down below as two equations. We now have our two equations with our two unknowns. And again, on the test, from this point on, it is your personal call if you would like to use the elimination method or if you would like to use the substitution method. It does not matter which one you use. Pick one and commit to it. It will get you the correct answer either way. So for this, I'm going to go with my personal preference. I'm going to go ahead and use the substitution method. So I am going to solve my first equation for, I don't know, we'll go with G. It comes first in the alphabet. So maybe off to the side, I'm going to make a note for myself. I'm just going to write out how that process plays out. I have 4G plus 4R. Now I'm going to solve this equation for G. I want to get G all by itself. So I'm going to go ahead and subtract 4R from both sides. Gives me that equals 4G. And again, I don't want 4G. I just want regular G. I'm dividing everything by 4. And let's see, what is that? Okay, so I have my new G value. I can write this in over here. Well, you have that. So I solved my first equation for G. I can now plug this in for G in my second equation, and then we'll be able to solve for R. And again, as the reminder, when you are going through these, whether you're using the substitution or the elimination method, it really does not matter which one you would like to eliminate or which one you would like to solve for. First, you're just finding one variable over the other, and you'll eventually find both of them in due time. So don't feel like you are required to solve for one over the other first with any of these problems. We'll go ahead and solve the rest of this out and get R all by itself and solve for that. So we get Ryan's rate is 465 blocks per hour. Okay. Now again, I have R. I need to find G. So I can go ahead and plug this back into either of our original equations. And again, the question was posed earlier, does it matter which one we pick? Absolutely not. I am going to arbitrarily choose equation 1 to plug this into, but you may totally choose the second equation. It is your call. Both will work. There we have Jeff's rate. Perfect. So our last thing, we just bring all of this together. We could do something like Jeff is 160 and Ryan is 465. And something like this for our final answer is perfectly acceptable. Maybe you want to write it in as Jeff's rate or Ryan's rate. Either of those work. I'd be perfectly happy with that. We're bringing it all together for our final answer there. So again, if you were noticing or thinking, hey, this looks very similar to the distance rate time problem, just adjusted a little bit for this, you are absolutely correct. It is the rate principle, which is the general thing that encompasses the distance rate time problem. We're just using that in a scenario where we're combining totals together to get an overall combined amount at the end here. Okay. So this is the last of the problems where we are going to be using a lot of the elimination and substitution method stuff to solve for the answer. We are going to jump over to do a GPA problem. And GPA problems are kind of their own beast. They're a little weird in that regard, and I will note that I'm not planning on giving you guys anything beyond the weirdness of what we have here in this example, or really test on this as a generality. It does show up in the homework, and we are technically required to cover it, so that's why we get to go through it now. The GPA ones, I generally do not give anything particularly too weird beyond what we have here. Let's go ahead and take a look at that. We'll scroll over. There we go. All right. So the first semester, Morty is enrolled at Green River College. He earned the following grades: C in a 3-credit English class, A in a 4-credit science class, B in a 3-credit speech class, and a C in a 4-credit psychology class. Rick thinks Morty should just drop out of college and join him on interdimensional adventures instead, because of course he would. With something like this, we are told that an A is equal to a certain GPA, B is a GPA, C is GPA, and so on and so forth with these. This can also be listed as he earned a 2.7 in a 3-credit class, a 4.0 in a 4-credit class, 3.2 in a 3-credit class, things like that. So I'm using A, B, and C here to help denote the GPAs, but these can also be written as 4.0, 3.0, 2.7, 3.8, 1.6, anything like that to represent a GPA there. So we have two parts with these. We want to determine Morty's GPA for his first semester, first and foremost, and then we're going to determine what he needs to do to raise his GPA to a 3.0, which we'll do after. So let's go ahead and get this set up for ourselves. Come on over here. There we go. All right. So for A, remember our general way of writing out GPAs and finding those, we need to add together the sum of all of the credit hours and then divide it by the credit points, I should say, and then we divide it by the total number of credit hours. Now, the weight associated with each class does matter, and the weight is equated, and we find that based on the credit hours that a class has. So, for instance, a 5 credit class versus a 2 credit class versus a 1 credit class, things like that. That's the weight that a particular class carries and therefore has as an impact in the overall final GPA calculation. So, adding up the GPA hours. So we were told that he had a C in a 3 credit English class. So that's going to be for a C, that's a 2.0. So it's going to be 2.0 times 3 hours. He had an A in a 4 credit class. So that's a 4.0 for 4 credits. He had a 3.0 in a 3 credit class. And he had a C, which is a 2.0 in a 4 credit class. So each one of these little things multiplying together here, each of these is the GPA, or like the score that he earned, times the number of credits that that class has. So it's always the formula that we're going to be using. Grade times credit hours for the numerator. Now the denominator is where we're going to be adding the credit hours together. So we were told that he took a 3 credit class, he took a 4 credit class, another 3 credit class, and another 4 credit class. We just have each of the hours adding together down below here. Now we can apply our calculator and we are going to simplify the numerator. We are then going to simplify the denominator, and then we're going to convert it into a GPA afterwards. So you could enter all of this numerator into your calculator, all of the denominator, and then we'll solve what's left over afterwards. Okay, and we're getting something, I'm getting a pretty big, long, gross, terrible decimal here. So let's go ahead and round this to 1 decimal place just to keep it consistent with the 2.0, 3.0, things like that we had here. So 39 divided by 14, that would be 2.78574, blah, 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 bunch of extra stuff. Not going to worry about that. We're going to go ahead and round to 1 decimal place. So this thing, therefore, is going to be a 2.8 GPA. So we sit at a 2.8 overall currently after his first semester. Awesome. We're asked in part B, he wants to raise his grade to a 3.0. How many credits with a grade of an A must Morty take to meet his goal? So we already know for part B, we know what the end resulting GPA is. So we want the result of this to be a 3.0. And again, we would need to set up all of the things adding together and all the credit hours adding together down below. So what you can do, I'm not recommending you do this, but what you can do is you can rewrite all of this up here and put it right down below with a little bit added on to it, which we're going to do shortly. And you can add all of this exactly as it is right down below here with a couple other things added on, which we'll do shortly. Your other option, and I recommend doing this instead, we know what all of this combines to. We know this entire thing is a 2.8 GPA with 14 credit hours. So I can bring both of those down and just fill that in right here instead of bringing all of this extra stuff. So what this looks like is his current GPA of 2.8 at 14 credit hours. We know he is adding on more credits. And we're told that the grade for those, we're asked, how many credits with a grade of an A must Morty take to meet his goal? We're told an A is 4.0. So we can put 4.0 here. And do we know how many credits that he's going to need to take to meet that goal? We have no idea. So we can leave this in as an unknown. You could put X. I'm going to put C in here for credit hours. But we know he has his current, oops, it's not changing the color for me. There we go. His current plus the unknown additional amount, that's going to be his new cumulative GPA that he would have. Now for down below, again, we're adding the credit hours together. So we know he has 14 hours already. We're adding on some amount C on top of that, and that's going to be my new total credit hours down below. And if you're looking at this thinking, well, hold on, I just have a single variable showing up in here in two spots. I don't have two showing up, so I can't use the elimination method or the substitution method. You are absolutely correct. Again, these ones are unique where we don't always need to use them. What we have instead here is a fraction equals a fraction. This 3.0 is the same as saying 3 over 1 equals this whole big gross fraction here. With this written out, a fraction equals a fraction, I can cross multiply. And what I'm going to get is 3.0 times the denominator of the other one. And I'm going to have 1 times everything in the numerator of the other one, which we can just leave as the way it's written. And now we can go through and solve this resulting equation for C, and then we will have our final answer. So I'm going to simplify each side of the equation, and then I'm going to start adding and subtracting to both sides to get to my answer. Okay. And from here, we are getting that he needs 2.8 credits to earn that 3.0. Now, here's the really, I think, kind of slimy way that these problems present themselves, and the last thing that we need to do. Have you ever seen a class listed in any college catalog that is a 0.5 or a 0.8 or a 0.6 credit class? We generally don't see those. So we can't have a partial credit class showing up here. So I can't round down because if I go below 2.8 credits, I'm not going to get that 3.0. But what I can do is I can go up to the nearest credit. So really, what does he actually need to get to the final answer? He needs 3 credits out of 4.0 to get to his final desired GPA of 3.0. So that's some of the weird stuff that shows up with GPA problems. I have put GPA problems on tests in the past, and I could put one on here for our upcoming test. However, I do not put problems that have anything weird like this showing up on them. It would be something more like this at the top, or something where if you're solving this out, it should work out to be a nice, hey, he needs 3 credits, or he needs 7 credits, or 2 credits, or something like that. You would get an integer answer here. The 2.8 round to the 3, no, that's just, it's a little too hand wavy for me, and we're not going to worry about that or have that show up. Okay. So with that, that is the last of the material for how we get to our 4 answers. I'm going to try and make sure there's some space here with this. So we can take a look at it here. But otherwise, that is going to be everything for our recording for today and for the material. So I'll go ahead and end the recording here if I figure out how to do that. And then I'll take any questions that you guys have over any of these or anything else that you guys would like to go through afterwards.